Okay, so the next thing that we're going to talk about in our discussion with electricity are circuits, what they are and how to draw some of the basic ones. This lesson is going to be more of an introduction / review on what you've learned in previous classes about circuits, but we are going to go in a little bit more depth in the future. So first thing we should probably talk about is what is a circuit? Well, a circuit. Why is this like a pale blue? Let me fix that. Hold on, that's going to be hard to read. What is a circuit? Okay, so a circuit is a set of electrical components that are connected with wire so that they create a path or paths for charges. So this is taking electricity and basically giving it a use or giving it a purpose so that it's being used in some way. A circuit needs to have two things. It needs to have a source of potential difference in energy. This is basically your electricity source, and this is sometimes called an electromotive force, or EMF for short. It's just another name for it. So basically everything that is a circuit needs to have some place for the electricity to come from. It needs to have something that is pushing the charges through the circuit. If you don't have that, it's not really going to be a good circuit. Another thing that they need is they need an element to use the energy. Oops. I'll format this the same way. And this is sometimes called a load. As long as your circuit has those two components, it's probably going to be just fine. There are different ways that you can connect circuits that are going to be different. This is bothering me that that's not capitalized. There we go. Okay. So let's go ahead and talk about what other criteria need to happen for a circuit to actually function. So it needs a source of potential difference, needs an electrical component. One thing it also needs to be is a closed loop. So we have two types of circuits. There are circuits called closed circuits. A closed circuit is a closed loop path. For electrons to follow. And I'll give an example of what that looks like in a second. An open circuit is an incomplete path which results in no current. Okay, so in order to draw circuits, we do need to have a common way of drawing these, a common way of illustrating them. And so there is a system that has been set up where you can actually create a diagram of a circuit called either a circuit diagram or a schematic diagram that shows all of the different components that are a part of the circuit. And the nice thing about them is that they're pretty much universal. So you can read a schematic diagram from anyone, and you should be able to read what all of the different parts are. Now, we're not going to go into every single possible symbol in this class. We're just going to go over some of the common ones. So let me go ahead and give you guys those. So a schematic diagram is a diagram that uses lines to show wires and symbols to show electrical components. Yeah, I like handwriting it better than typing it. I regret doing that. Okay, so let me go ahead and give you guys a table of some of the more common symbols that you see. So in this column, I'm going to write what the component actually is. And in this column, we're going to write the symbol for it. Okay? So the first is a wire. So if something is a wire, the symbol for it is just going to be a line. Pretty easy. Sometimes the line might be like a bent line if it's a corner, but any line that is connecting different components together is just going to be a wire. Also, resistor. So a resistor is just it's an electrical component that slows down the flow of electricity. Usually they end up taking the electrical potential energy from the battery and converting it to heat or even sometimes light. And a resistor is a zigzag line on a schematic diagram. Okay, so that zigzag line is supposed to show that it's slowing down the current that's going through. All right, well, what if it's a light bulb? So first off, a bulb is technically just a resistor. So a simple light bulb has a tungsten filament in the middle that is resistant to electricity going through it, and it glows. So a bulb is really just a fancy resistor, but to make it look different, what we do is we take the resistor symbol and we just encase it in a circle. Okay, so a light bulb looks like that. All right, well, what if something is plugged into the wall? What if that is your source? So if something is plugged into the wall, the symbol for that is going to be a long line and a short line encased by a circle. So if you think about the way that an electrical plug looks when you look at the prongs on it, there's one longer and one shorter prong. That's supposed to be kind of illustrated here. What if it's just a battery though? Well, battery is the same as a plug, just without the circle. So it looks like this. The longer side, by the way, is the positive side of the battery. The shorter side is the negative side of the battery. This here is just when you have one single cell battery. But you'll notice that a lot of times when you open up the back of a remote control or your calculator, you'll notice that there is more than one battery there. When that's the case, it's called a multi-cell battery, and you basically have one set of lines for each battery that is there. So this is a multiple cell system. Okay, make my table a little bit bigger here. Almost done. Just a few more. The next thing that commonly shows up is a switch. A switch is just a really easy way to change a circuit from between closed and open. So when you open the switch, it will open that part of the circuit. And when you close the switch, it will close that part of the circuit. And these are shown with just like a hinged line. So this one here is an open switch. If the switch is closed, it will look like this. So it's kind of like a door. That's how it appears. And then the last thing that sometimes shows up is a capacitor. This is not going to be something we really see too much of. But a capacitor is an electrical device that has two plates that are separated by distance. And basically what they do is they build up an electric field between the two plates, so they can store a charge that way. Okay? So that's what a capacitor looks like, and it's two equally sized lines. That's how you know it's different from a battery. All right, so those are the different components of a schematic diagram. Let's go ahead and draw a simple one so I can kind of show you. So we have our closed and open circuit definitions up above. Let's go ahead and draw an example of a closed and an open circuit, just so we can practice our schematic diagrams and also just kind of work with those definitions. So a closed circuit is a closed loop path for electrons to follow. So the first thing I need to do is add in a EMF. So I'm just going to do a simple battery. Okay, so there's a positive side, there's a negative side. There's my battery. I'm going to go ahead and draw a few things in it. So maybe there's a resistor here, and then maybe like a light bulb. And let's go ahead and add a closed switch. I said this was a light bulb, so I should put a circle around it. There we go. So this would be an example of a closed circuit. So electricity is going to run this way around the circuit. This is the way the electrons are going to go. They're going to go through the resistor, around this corner, through the light bulb. They're going to go across the switch and then into the other side of the battery. So it's a closed loop. There's only one path for this one, but it is a closed loop path. Now, if it is open, why don't I just go ahead and copy this, but open the switch? Oops. Stop it. There we go. Okay, so if I open this switch here, now there's going to be no way for electricity to flow because there is no closed path. In order for electricity to flow, all of the electrical components need to be connected to both sides of the battery, not just one side of the battery. A battery provides a source of a potential difference. So both of the sides of the battery are separated by a different potential. So if they're not connected to both sides of the battery, they aren't connected to a potential difference. Okay? All right, so what happens if there is no load on the battery? So what if I have a circuit that looks like this, where I have a battery and it's just connected like this? So the resistance of the wire that connects to two sides of the battery and the resistance of the battery itself is usually very, very, very small. So if there is no resistance, what that does, according to Ohm's law, if you have a really, really small resistance and you're dividing the voltage by a really small number, what that can actually do is increase the current to a very high amount. So if you don't have a load in your current, it can actually create a very dangerous situation where the amount of current can become unsafe. This is called a short circuit. When you have a circuit that is short circuiting, it will generate a lot of energy in the form of just like heat. That heat can burn out electrical components, and it can also start electrical fires. So a very common example of thinking about this would be like if you spilled water on your laptop. When you do that, the water, because it is a conductive substance, it will actually provide a shorter path between the two sides of your computer's battery. When that happens, your computer short circuits. So that's why water is a bad thing to have with electronics, because it creates short circuits. Also, if you take two wires and you touch them together, it will create a short circuit because it's bypassing any loads that those wires may be attached to. Okay, so it's not a good thing. You want there to be some amount of resistance within your circuits so that they can help dissipate the energy that is being created. Okay? All right, so I said a minute ago that batteries have a very small internal resistance. This is true. So the voltage that you read on a battery, the EMF that you read on a battery, is actually going to be smaller than the actual potential difference that you read. However, the internal resistance of a battery is going to be really small, so we can usually ignore it. Okay, so how does a circuit work? So we're going to talk about the conservation of energy a little bit in this. So let's say I have a circuit that is like this, just a simple circuit. Let's say that I have a 1.5 volt battery, okay? This is going to be the voltage for any of the batteries that have an A or a AA or like a letter for their size. So AA, AAA, C batteries, D batteries, anything like that where it's a letter, those are all going to have the same voltage of 1.5. What makes them different sizes is actually how long they can be used. So it's basically how much chemicals they have inside of them. So a AAA battery will not last as long as a D battery, but they provide the same amount of voltage, okay? All right, so that aside, when you have a voltage of a battery and you know the voltage of that battery, that's basically taking chemical energy or chemical potential energy and changing it to electrical potential energy. Okay, that electrical potential energy is going to transfer to whatever is connected to it in the circuit. So the resistor is going to use up that amount of electrical potential energy. Now, what that electrical potential energy is converted into kind of depends on what's connected to it. If it's a light bulb, we'll go ahead and say it's converted to heat and light energy. All right, so that's kind of the chain of energy. We know that energy is conserved, which means the total amount of chemical potential energy we started with is going to be the same as the amount of heat and light that is produced. So if I have like 7 joules of chemical potential energy here, I know I'm going to end with 7 joules of heat and light energy at the end. You can't destroy energy. It's always going to be conserved. Because potential voltage is a measure of potential energy per unit charge, what that means is that my resistor or my bulb is going to have the same voltage across it. And that's just because energy is conserved. So I know that if it is also dealing with 7 joules of energy, and because voltage is a measure of potential energy in a way, it has to have the same voltage as well. So if you know the voltage of your battery and you have a simple circuit like this, then you also know the voltage across your component, okay? What if you have a slightly more complicated example? Well, there are two ways that you can connect electrical components in a circuit. They're called series and parallel. So I'm going to make a table here. So the first thing I want to put in my table is a definition of each. So what makes a series circuit different than a parallel circuit? So a series circuit is a circuit in which all of the components are combined in such a way or connected in such a way that there is only one path for electrons. A parallel circuit is a circuit in which components are connected so that there's multiple paths. So let me draw a picture of each so you can kind of see what makes them different when how they appear. So for series, say you have your battery here. If you have say you have like two resistors in series, it might look like this. Okay? So you can see here that there is only one path for the electrons to follow. They're going to be going technically this way, the way I have it drawn. They're going to go around the circuit, but there is only one possible path for them to go, for them to reach the other side of the battery. Okay, so it's just one simple closed loop. A parallel circuit, you might have something that looks like this, where you have your battery. Then here at this point, your wire might branch, and each part of that wire has a resistor, and then they reconnect here and then go around. So when you're looking at how your electricity is flowing, it's going to start here, it's going to go this way. Some of the electricity will go through this path, some of it will go through this path. And then they will recombine at this point right here and then go to the other side of the battery. So there's more than one possible way for the electrons to move. They can move through the first branch or they can move through the second branch. That's what makes this a parallel circuit. All right, well, let's talk about some of the different characteristics of series and parallel circuits. So first off, if you are talking about a series circuit, because there's only one path for the electrons to follow, when you're looking at the total current, it is going to be the same at the beginning at the battery as it is in each of the resistors. So if this is like R1 and this is R2, resistor 1 and resistor 2, the current is going to be the same through each of those because there's only one path for the electrons to go. So if you measure the current here and it's 0.25, and then you measure the current here, it's also going to be 0.25 because there's only one path. You can't split the current down multiple paths, so it's going to be the same through each. Okay, what about a parallel circuit? So in a parallel circuit, the current is going to be split. However, you can't really get rid of current or electrons, so the total current is just going to be equal to, if this is R1 and R2, the sum of both of them, so I1 plus I2. So say you have a current of like 1 amp, maybe you have like 0.3 amps go through this one, then you'll have 0.7 amps go through the second one. So it splits up a little bit, not always evenly. So here I don't have it split evenly. It doesn't always split evenly. Some of it will go through the first path, some of it will go through the second path, but the total is still 1 amp, okay? I'm gonna get rid of these red arrows so this is a little cleaner. Okay, so that's current. What about voltage? When you are looking at two things that are connected in series, we know that the total voltage is, going to be given to us. So say it's like 1.5 volts like it was before. Now that energy is going to be used with R1 and R2, but because they are on the same path, that energy is going to be split between them. So the total amount of voltage that you have is equal to R1 plus R2. Oh, V1 plus V2, sorry. So you might have maybe like 0.5 volts being used here, but then 1 volt being used here. So they add to the total voltage. Some of it will be used up in the first resistor, some of it will be used in the second resistor, okay? Now for parallel, this one you have to kind of think about. Both of my resistors are connected to the same 2 points. So right now it kind of looks like R2 is on a different, it's like connected at 2 different places in R1, but they're not, okay? R1 and R2 are connected to those 2 highlighted points. So that means the difference in potential is going to be the same for both of those because they're connected to the same 2 points. So the total voltage is equal to the voltage across the first resistor, which is equal to the voltage across the second resistor. So if this is 1.5 volts, this will also have a voltage of 1.5, and this will also have a voltage of 1.5. Okay? Now finally, resistance. So if I have multiple components in my circuit, one nice thing that you can do is figure out the total resistance in your entire circuit. If you know your total resistance, you can use that information to find other information like ITotal. So the total resistance is called equivalent resistance. So I'll write that down here. This is when you combine multiple resistors to find the total resistance. Okay, so for a series circuit, the equivalent resistance is just going to be the sum of the 2 resistors, or more if you have more. Guess I should make all of those applicable to more than 2. So if you had a resistance of like 2 ohms on R2, but then you had a resistance of 1 ohm on R1, the equivalent resistance for the entire circuit would be 3 ohms, 2 plus 1. So pretty easy to find when it is in series. When it is in parallel, it's a little bit more complicated, and let me show you where it comes from before I write down the formula. So I know that the total current is equal to I1 plus I2. I also know, because of Ohm's law, that voltage divided by resistance equals current. So I can substitute that in. Like that. Now, because I know for parallel circuits that the voltage is going to be the same for all of these, I can actually get rid of that term completely and just replace it with a 1. So dividing both sides by the voltage. And this is what you get for the equation to find the total resistance for things that are connected in parallel. It's a reciprocal relationship. So 1 over the equivalent resistance equals 1 over R1 plus 1 over R2. Okay? All right, so one more thing that I want to say about series and parallel circuits before I move away from this is that for a series circuit, because everything is connected so that there's only one path for electrons, if any part of your series circuit breaks or a switch is opened, your entire circuit is going to stop working. So all elements must be functioning for the circuit to work. Okay, what about parallel? Well, parallel, because there is more than one path, as long as your electrons have a path to go through your circuit, that path is always going to be functioning. So as long as there's still a functioning closed loop path, the circuit still functions. Okay, so let's do some practice finding equivalent resistances. So for my first practice problem, let me switch to a different color. For my first practice problem, let's say that I want to know what is the equivalent resistance and the total current in this circuit. So let's say I have a 9-volt battery. I have a 2 ohm resistor here. I have a 4 ohm resistor here. I have a 5 ohm resistor here. Oops. I have a 7 ohm resistor here. And they connect back at the beginning. Okay, so when you are looking at this circuit, you can see that it is a series circuit because there's only one path for the electrons to follow. So remember, for a series circuit, the equivalent resistance is just found by adding together the resistances. So the first resistor is 2 ohms, the second is 4 ohms, then 5 ohms, then 7 ohms. If you add those together, you get a total of 18. Okay? So the equivalent resistance is 18 ohms. To find the total current then, what you're going to do is look at your battery and see what the voltage is and use Ohm's law to solve for the current. So remember, V equals IR. So I equals V over R. So I total equals V total over REQ, which is 9 volts divided by 18 ohms, which is 0.5 amps. Okay? So your equivalent resistance can be used to figure out the current going through your circuit as well. And that's because we know the voltage of the battery. All right, let's do another one. Let me move this over. I'll move it there. Let's do another one. And I'm going to be answering the same question here. For this one, say that I have a battery. It is connected to a 7 ohm resistor, a 5 ohm resistor, a 4 ohm resistor, oops, and a 2 ohm resistor. Okay? So looking at this one, you can see that there are 4 paths for the electrons to follow. So this circuit is a parallel circuit. I'm going to still give this a 9 volts for voltage. So to find the equivalent resistance, I have to use the parallel equation. Okay, so if I take all of those fractions off to the side, so 1/7 plus 1/5 plus 1/4 plus 1/2, what you end up getting is 1 over REQ equals 1.09 rounded. So then to find REQ, you take 1 over that number. Which is 0.917. Okay, so I found the equivalent resistance of all of the resistors put together. Now to find the total current, I do the same thing that I did before. Nine volts divided by 0.917 ohms. And you get 9.8 amps. Okay? All right, so I want to point out a couple of things about this problem. So a lot of things are similar in this problem. So we have the same resistors, the same battery, but you can see the 2 answers that we got for resistance and for current are very different. So for resistance, whenever you have resistors that are added in series, as you add resistors, it's going to just increase the total resistance as you keep adding them. But you'll notice that for a parallel circuit, the resistance that you get at the end, 0.917, is actually smaller than all of the resistors that were added. So by adding resistors, we actually lowered the total resistance. And that actually happens because of the multiple paths. So by giving the electrons multiple paths to go through, even though we added a load onto the circuit, we've overall decreased the amount of resistance because there are more paths for the electrons to follow. So they have more freedom. Okay, so let me go ahead and add that to the table because that's pretty useful information to have. move this down. Oops. There we go. Okay, so for a series circuit, as you add resistors, it increases the resistance. But for a parallel circuit, adding resistors decreases the total resistance. Okay, and that's just because of that reciprocal relationship that we have. Because it's 1 over REQ, the bigger you make this side, the smaller REQ is going to end up being. Okay? All right, so that pretty much does it for our introduction. Go ahead and get started on the lab. It's a fun one. Enjoy it.